Hi, hello friends, welcome back to Power Electronics revision class. So in this class, we are going to complete the complete formulas and the tricks which are very important in our Power Electronics subject. We know Power Electronics is a really very important subject in examination point of view. We can expect minimum 10% of the questions out of 100% in any competitive exams because it is our core subject. So let us start without wasting our time. The first one is power diode. What is the basic difference between the power diode and the signal diode? The power diode is having high voltage, high current, high power handling capacity, and it will be usually operated to power frequency. In our Indian system, power frequency will be 50 Hz. For European system, it will be 60 Hz. So next thing is this diode will operate whenever the value of anode voltage will become higher than the value of cathode voltage. It will be entering into forward bias. In the alternative case, it will be entering into reverse bias. Next, if you talk about the reverse recovery characteristics of the diode, see here I have drawn the waveform with respect to time period. If you observe the current flowing through the diode, so this is the reverse recovery characteristics here. In reverse bias, this is the maximum current that we can observe in the reverse bias. And here you can observe in reverse characteristics, we will be talking about two types of time period. One is the current is trying to reverse the direction and trying to achieve its maximum value, and then it is slowly decaying to zero. So we are dividing it into two parts. One is TA and dB. Here its corresponding current is called IRM. Now further, if you observe the total reverse recovery time TRR, that is the addition of TA plus TB. From this we know if you observe the value of TA, it is always higher than the value of TB. So approximately I can ignore the value of TB. So the value of TRR will become approximately equal to TA. Then further I can write down the expression for IRM equal to TA into dI by dt, and the QRM will become half TRR into IRM. Here, if you are substituting the value of IRM, that will be giving you the value of QRM. Further, you can calculate the value of reverse recovery time from this. And after that, you will have to remember softness factor. It is the ratio between TB by TA. Whereas if the value of TA will become equal to the value of TB, then the value of softness factor will be equal to 1. Suppose if the value of TA will be far greater than the value of TB, then it is become SF, that is softness factor value will become less than 1. See, the good one is SF should be less than 1. That is called fast recovery devices. So the value of softness factor always should be less than 1. That is what we are calling as fast recovery. System will be fastly regaining. So that is called fast recovery. So let us revise other things. So this is all about power diode. Now we'll be talking about SCR. So SCR is the developed version of diode. We know it is having four layers P, N, P, N. Here I have taken P, N, P, N diodes. So it will be having three junctions: junction 1, junction 2, junction 3, and it is also having three terminals: anode, gate, and cathode. Now, based on the junction, see each and every junction you can observe a diode structure. PN, in junction 2 we will have NP, in junction 3 we have PM. So totally there are three types of diodes we will be observing in the internal structure of the SCR. So now based on the junction diode characteristics, we will have different types of operating mode for SCR. The first one, if the junction 1 in forward bias and the junction 2 is reverse bias, junction 3 is in forward bias, then that is called forward blocking mode. If all are in forward bias, then that is called forward conduction mode. If first one is reverse bias, junction 1 is reverse bias, second one forward bias, third one reverse bias, then we are calling it as reverse blocking mode. Now here in SCR, we will have to recapture the definition for latching current and holding current. Latching current is related with the turn on process, whereas holding current is related with the turn off process. Latching current, it is the minimum current required to just above which, so it is the minimum amount of current that is flowing into the thyristor above which our system will be turned on. Whereas holding current, it is the minimum amount of current that is attained below which your whole system will be turned off. So during the turn on process, we are trying to force the thyristor to go below this holding current value such that your device will get turned off. Whereas when the moment you are turning on the device, we are trying to force the thyristor to carry the current above the value of latching current such that it will be in on state. That's all. Now always you can observe this, the value of latching current is higher than the value of holding current for SCRs. Next, so there are two types of times that we are always observing in our SCR and its circuit. First one is circuit turn off time and another one is SCR turn off time. Here the condition for success combination is always the value of circuit turn off time must be higher than the value of SCR turn off time. That is called a successful combination. Next, let us discuss about the gate characteristics of the SCR. So while designing the SCR, the very important thing is it is having two terminal, one is anode and another one is cathode. Apart from this, we will be also having one more terminal that is called the gate. So controlling the gate is very important for us. Here I have drawn the equivalent circuit of the gated terminal, how it is connected to the DC supply and its correspondent formula, because most of the times question has been directly framed from the gate and its correspondent equivalent circuit and its power that has been being dissipated across the thyristor. So these are all the formulas that I have wrote and I have given its correspondent equivalent circuit also. While solving the problem, just to remember these relations and its correspondent KVL equation that I wrote here, it will be very easy for you to crack the question. Now, when we are talking about different types of triggering methods in SCR, of course, we are having forward voltage triggering, dV by dt triggering, and then gate triggering. Then we are having light triggering, temperature triggering. Out of this, all this method, which is the most peaceful method for our power system. See, in power system, nowadays people started adopting with the HVDC transmission lines, we know. So, especially in HVDC transmission line, we will be using light triggering. That is one of the interview question. So, next. The another one is SCR Production. So we have seen here triggering methods of the SCR. Now let us cover the SCR Production. So there are different types of protection for SCR. See, where is our SCR? This is our SCR location. Now you can observe there is some heat sink. This will be placed on the top of the SCR anode terminal. Here this will be used for thermal protection. Similarly, you can observe SCR is connected in series with the inductor, that is for di by dt protection. Like when there is a sudden change in the value of current with respect to time period, that sudden spike can be protected, right? Our SCR will be protected away from that sudden spike with the help of inductor. Similarly, if there will be a sudden spike in voltage, then that can be avoided, or that from that dV by dt changes, our SCR can be protected with the help of this number circuit. Suppose if there will be a change in huge voltage, if suddenly a huge amount of voltage will be dropped or appeared across the SCR, then with the help of varistor, we can give protection from the over voltage. Similarly, when there is a huge amount of current is trying to enter into the SCR, then we have a separate over current protection fuse circuit that will be taking care of give protection for your SCR from the huge value of current. Now let us talk about gate terminal. In gate terminal, we will be having different types of circuits you can observe. For the gate terminal also, giving protection from the high value of current is very important. So here you can observe there is a resistor. This resistor is giving protection for the gate away from, that is, high value of current. This is called over current protection. This is used for over current protection. Next, for over voltage protection, we will have a Zener diode. It has been connected across the gated terminal. You can observe this. So this is for over voltage protection. Next, if there will be any noise that has been injected, some noise spikes will be introduced on the gated terminal, that can be avoided or that can be suppressed with the help of RC coupled circuit. You can observe here. So these are all the types of the protection that will be usually giving for the SCR. Next, let us discuss about heating and the cooling methods. Here you can observe that on the SCR top plate, on the anode side, you can observe there is a heat sink. So here, how it is effectively giving the thermal protection, how the temperature is being dissipated. So let us start from the beginning. So actually, we are starting from the junction of the SCR. After that, it will be shifted to case. From that, it will be going to sink. Then it will be converted as an ambient temperature, atmosphere. Now here, theta indicates the resistance equivalent. So that is called a thermal resistance. I wrote it here. Now, T indicates the temperature equivalent. In electrical, we are calling it as voltage. In electrical, temperature. Theta is called resistor. So here it is called thermal resistor. Here the average power. In electrical, this is the equivalent value of current. Now, according to Ohm's law, if you simply relate, we know I is equal to V by R. Now, in place of I, we have V average. In place of V, we have temperature. So, in place of R, we have thermal resistance. That's all. Now, how to calculate this average power? You can see I have drawn the complete equivalent circuit, thermal equivalent circuit. So, from here, if you want to know the total current, then find the total potential difference between Tj and Ta, that is ambient temperature versus Tj. So, Tg minus Ta by total resistance, or the individual resistor you can focus. The difference between junction temperature minus case temperature divided by the resistance, thermal resistance available between the node. Similarly, between these two nodes you can calculate. Similarly, between sink and ambient also you can explore. So these are all the different approaches we have to observe when we are talking about heating and cooling of the SCR. Next, let us see the series and the parallel connections of SCR. See, the first thing is, while talking about the series connection, it is very important when the moment we are connecting more than one SCR in series circuits, The first most important question is you will have to explore the string efficiency. These type of calculations you might have observed in our power system. Like when we are connecting the more number of insulators in series, we will be repeating the same procedure. Yes or no? Yes. So there also we have been explored the value of string efficiency. Same formula, nothing is there. So here also you can take, this is our insulator 1, insulator 2, insulator 3 from the terminal. Like that, here also from the terminal, this is thyristor 1, this is thyristor 2, this is thyristor 3. Now, how we will be calculating the string efficiency? We will have to observe the total voltage, sum of all the voltage. It will be rise in the numerator divided by n indicate the number of thyristors. How many thyristors are there? 1, 2, 3. Totally we have 3 thyristors into the initial voltage, first thyristor across the voltage, that is V1. That is the formula to calculate the string efficiency. Similarly, we will also requested to calculate the value of static resistance and the dynamic capacitance for the series connection of the SCR. So here I wrote the formula and I have written clearly what are the things that we are considering here. Similarly, for the capacitance, I wrote the formula, and DRF indicates the derating factor. Sometimes it has been asked in examination just to calculate the string efficiency and then subtract to 1 minus string efficiency. That will be giving you the value of derating factor of the thyristor. Got it? Next, so let us discuss about other people. We have completely revised the basics of thyristor. Now, let me bring the difference between BJT, MOSFET and IGBT. So, it comes to picture, if you can observe in the screen, the difference between BJT, IGBT, MOSFET. First thing, BJT is a bipolar device. Yes. And when we are talking about MOSFET, MOSFET is a unipolar device. And in case of IGBT, of course, it's a unipolar. Similarly, if you talk about the input impedance of the BJT, it is always very low, whereas for MOSFET and IGBT, it is always very high. And while coming to the amount of, that is charge carriers about BJT, MOSFET and IGBT, always remember, in BJT, you can observe, it will be always carrying both positive and negative charges. If your device is trying to carry both positive and negative charges, then simply we are calling it as minority charge carrier device. If your device is trying to carry only one type of charges, then we are calling it as majority. So when I am talking about the MOSFET, MOSFET is a majority carrier device, whereas IGBT, BJT, diode, all are thyristors, all are acting as a minority charge carrier devices. Now, in the temperature coefficient point of view, NTC, that is negative temperature coefficient, PTC, positive temperature coefficient, positive temperature coefficient. BJT is a negative temperature coefficient, whereas MOSFET and IGBT are acting as a positive temperature coefficient. Similarly, when we are talking about BJT, we know it's a current controlled device. With the help of base current, we are controlling all this. Yes. Whereas MOSFET and IGBT, we are having gate field voltage, separate voltage. So it is acting as a voltage controlled device. MOSFET and IGBT are acting as a voltage controlled device, whereas BJT is a current controlled device. So I have covered all major points between the difference between all these three people. Let us talk about the diode characteristics. Like if I am taking a diode and on the input side we will be connecting it with the DC supply. On the output side we are connecting the RL circuit. So whenever you are observing these type of circuits in the examination, just you'll have to remember the current expression and its corresponding time constant, that is tau indicates the time constant, and the voltage drop across the inductor, and then what is the value of DIL of 0 plus by dt, initial value. For that, you will have to go through the supply voltage divided by inductance here. Whereas here, the conduction period, beta, indicates conduction period. So expected conduction period for the RL circuit, it lies between pi and 2 pi based on the value of the inductance that we are choosing. Similarly, suppose if I am taking pure inductance, then current expression, conduction period is the most important term. For a pure inductor, the conduction period will be 2 pi. In equivalent, I can say 360 degree, it will be in conduction only. And on time will be what? 2 pi by omega. Because we have seen it is conducting for 360 degree. No, it will be terminal for whole 360 degree. Next. And one more thing here, see if you observe, whenever we are connecting RL circuit with the DC supply, initially it will be acting as an open circuit because there will be no any energy. Whereas at the steady state, it will be acting as a short circuit. Open circuit, we are calling it as the property of insulator. Open circuit means current will be 0. Current will also be 0 in insulator. So the RL circuit, initial behavior of the RL circuit with the DC supply is like an insulator. The final state behavior of the RL circuit with the DC supply is like a short circuit. Short circuit means perfect conductor. We can call it as perfect conductor. So at the final state, RF circuit is behaving as a perfect conductor. Initial state, it is behaving as a perfect insulator when it is connected with the DC supply. Similarly, for RC circuit, if you are repeating the same thing, once again, see, this is our RC circuit. Yes, when it is connected with the DC supply, I have written the voltage expression, corresponding time period, current expression, and initial relation. Now, from this, the most important thing is time constant tau can be explored as R into C. Yes. Now, if you observe from this initial voltage expression, dVc of 0 plus by dt, this can be explored with the help of supply voltage divided by RC. So here RC is nothing but time constant. Yes. So from this expression also you can explore the value of time constant when RC circuit is coming to the picture. RC circuit is initially acting as a perfect conductor, short circuit. Finally, it is acting as an insulator, open circuit. Next. So let us discuss about the capacitor circuit. When we are talking about LC, not capacitor, LC circuit, in case of LC circuit, you will have to be a little bit conscious because there are so many important things will be coming to the picture. The first one is, when the moment we are connecting the DC supply on the input side for LC circuit, output will become AC. If you observe, the expression for current will be sinusoidal and the expression for voltage will be cosine. So this is the beauty of LC circuit. I have been connected these storage elements with the DC. So input is pure DC, but output on the output side, because of the nature of the oscillations between the storing and the discharging properties of the inductor and the capacitor, are producing the generating sinusoidal and cosine signals on the output side. So that is the beauty. So here I have given the expression for voltage across the inductor VL of T, voltage across the capacitor, and see if the initial voltage VC not indicate the initial voltage. If there will be no any information about the initial voltage drop across the capacitor, you can treat it as zero voltage. So this term will be disappeared. You will have only this expression. And if somebody will be asking you maximum peak inverse voltage of the diode is, that is supply voltage, it will be equal to supply voltage, and maximum voltage drop across the capacitor will be twice of the supply voltage. See there. You can observe at omega t equal to pi, you can observe the maximum voltage drop across the capacitor. If you are putting omega t equal to pi, cos pi will become -1, minus of minus will become 1, minus of minus 1 will become 2. So you will be having twice of supply voltage. That is the maximum voltage across the capacitor. Whereas since it is the LC circuit, it will be generating, it will be the frequency offered by the circuit is resonant frequency, that value is equal to 1 by square root of L into C. Next, what will be the conduction period of the LC circuit? The conduction period will be pi by omega R. Right. Next, if you are talking about the conduction period of the capacitor, it will be 90, right? 90 degree conduction angle, and for the pure resistor, the conduction angle will be 180. See here, I have not given, no, this is RC circuit. For RC circuit, we have seen the all properties. Like when we are talking about C circuit, the most important thing that you must remember is conduction period for C and the resistor R. Okay. Next, if you are talking about further, see, this is LC circuit. This is all its continuation. The value of IC of T, including initial voltage. Here I have already given the expression for current flowing through the circuit, that is IC of T only. But here I wrote without considering the effect of initial voltage. This is maximum current flowing through the capacitor or through the circuit. So here Vs only there because I was assuming that initial voltage is 0. If you are considering the effect of initial voltage, then this will be the formula. And this will be the maximum peak current. So this will be the maximum peak current. Similarly, so this is ICP value. Yes, that is maximum peak current. I have wrote already separately. And the peak inverse voltage across the diode will become Vs minus Vc naught if it is given, if it is not equal to 0. This is the formula. Next, let us discuss about SCR based circuits. First, we are going to design the circuits with the help of SCR. So let us start from the beginning. First one, half-wave rectifier. When we are talking about the half-wave rectifier, if you are connecting the R load, this is the formula for V naught average. This is the formula for RL load. See, I have covered all the formulas. Just to be attention and to make a note properly. So this is the formula for V naught average in case of R load. This is the formula for V naught average for RL load. Half-wave rectifier single phase. This is single phase. Sorry. Yeah, this is single phase. Now, when we are talking about RE load, I wrote this is the formula for V naught average. Remember, whenever we are talking about E type of load, if your battery is connected with the output terminal, RE load or RLE load, always the suggestion is first go ahead with the I naught average, such that you can easily save your time. You can easily explore the value. After that, calculate the value of V naught average. Similarly, here the value of theta and alpha both will become equal. So theta we know, right? Vm into sin theta equal to battery voltage E. From this you can explore the value of theta. Theta is equal to sine inverse of E by Vm. So this is the formula for theta. So I wrote theta equal to alpha here. Fine, sir. Next term. RL load, RLE load. So here this is the formula for RE load. For RLE load, once again, this is I naught average. I wrote it here. After that, same relation. You can use the same formula to calculate the value of V naught average for RLE load. Next. So once again, we are in single phase half wave rectifier. RL load with the freewheeling diode. Initially, I had given the formula for RL load without freewheeling diode. If I am considering freewheeling diode, then this is the formula. Next, let us discuss about full wave rectifier. Full wave rectifier R load, V naught average, RL load, V naught average given, RE load, V naught average given. So always remember RE load. For E type of load, I told first to go ahead with the I naught average, then calculate the value of V naught average. Similarly, RLE load. In RLE load, we'll be having two different formula. One is for conduction period and another is for disconduction period. So if the period is discontinuous, if your circuit is having discontinuous connection, here I have given the maximum conduction angle. This is the maximum conduction angle, this is V naught average. And this is the maximum conduction angle, this is V naught average. For discontinuous connection in case of RLE load. Got it? Next, RLE load with the freewheeling diode. This is the formula. Pm by pi into 1 plus cos alpha. Next, let us talk about semi-converters. Semi-converters means what? Your circuit will be it is having the combination of diodes and the thyristor. That is called semi-converter. It is having diode as well as it is also having thyristor. That is called semi-converter. You know, right? So here we will be having the load and we will be connecting the sources. Fine, sir. So when we are talking about semi-converter, we will be having two types of configuration. One is symmetrical configuration, asymmetrical configuration. Anyway, V naught average will be remain same for both of these circuits. It will not change. Next, let us come to three-phase circuits. Three-phase half-wave rectifier. In half-wave rectifier, always we will be having two different zones, alpha less than 30, alpha greater than 30. So this is the formula for V naught average in case of if the value of alpha is less than 30, and this is the formula for V naught average in case of alpha greater than 30. But remember, this formula is only applicable for R load. When I am talking about RL load, irrespective of the value of alpha, it is always 3 VML by 2 pi into cos alpha only. 1 second. Yeah. See, if you observe for RL load, only one and only formula. There will be no any alpha less than 30, greater than 30. Such a type of condition will become only for R load. For R load, alpha less than 30, we have a separate formula. Alpha greater than 30, we have a separate formula. Whereas for RL load, one and only formula irrespective of the value of alpha. Let us discuss about three-phase full wave rectifier. This is the formula. See, in three-phase full wave rectifier, once again for R load, alpha less than 60, alpha greater than 60. So when we are talking about alpha less than 60, this is the V naught average formula. Alpha greater than 60, this is V naught average formula. Once again, this is only for R load. Next, if I am talking about RL load, the one and only formula is 3 VML by pi cos alpha for all value of alpha. Next, let us discuss about three-phase semi-controlled converters. For RL load, I wrote only important formulas for semi-converters. RL load, this is the most repeated formula in the examination, just write down. For RL load, in case of three-phase semi-converters. So this is the formula. Next, let us talk about the circuit with the source inductance. We know rectifier circuits with on the input side, if you are considering the effect of the source inductance, then what will happen? Let us see. First one, in that case, if you are talking about one pulse converter, means a single phase half wave rectifier. This is the formula. See, this is the formula for V naught average with the LS. If I am considering the effect of source inductance, this is the formula. We already know for the general formula for single phase half wave rectifier without the value of source inductance. Yes. Now, by subtracting these two, you can find out the difference. With the inductance, what is the voltage? Without inductance, what is the voltage? So, what is the change in the value of voltage? So, delta V naught, it's nothing but the difference between V naught average without LS minus V naught average with the LS. I just wanted to know the difference. By considering the effect of the inductance, what is the voltage? Without considering the effect of the inductance, what is the value of voltage? So I just wanted to know the difference between them. So this is the formula to know the difference between them for one pulse single phase half wave rectifier. Similarly, for two pulse, I wrote it here. Just pause the video and make it notes clearly. Similarly, when we are talking about three phase half wave rectifier, I wrote everything clearly. Just pause the video, note it down. Similarly, when we are talking about 6 pulse converter, here I wrote the formula for everything. Just to see. For 6 pulse converter, V naught average, I wrote separately. V naught average can also be written in this way, one formula, or else the alternative formula, you can also write down this one. Both are giving the same answer. So according to the based on the given data that will be given in your examination, you can go ahead with its corresponding formula. Now the most important factor is for the 6 pulse converter voltage regulation formula. VR stands for voltage regulation. Here I wrote the formula for voltage regulation for 6 pulse 3 phase full wave rectifier. Now let us enter into the RMS calculation. So far we have done only V naught average. Here I will be bringing the important RMS formulas for different variety of loads that has been often asked in your examination. I have covered only important formulas that is repeatedly asked in your examination. First one, when we are talking about single phase half wave rectifier, R naught V naught average formula, RL naught V naught average, sorry, not V naught average. So this is VRMS. I made a mistake, right? So just to correct it. This is RMS voltage. Next, when we are talking about RL naught with the freewheeling diode, since we are in single phase half wave rectifier, this is the formula for V naught RMS. Let us talk about full wave rectifier, R naught V naught RMS. I wrote it here. Next, RL load V naught RMS, written RLE load V naught RMS. Again, see, this is RLE load. Here I wrote, but here also I wrote RLE load only. But with the freewheeling diode, what is the value of V naught RMS? Most important formula, just note it down. Next, let us talk about semi-converter single phase. In case of semi-converter, it doesn't matter whether it is symmetrical or asymmetrical configuration. We have a single formula for V naught RMS. Just make a note. Next, let us talk about three-phase half wave rectifier. For R type of load, I wrote it here, R load, RL load, RLE load. The common formula is this one. But for R load, we have different conditions. If alpha is less than 30, this is the formula. If alpha is greater than 30, then this one is the formula. Remember, for all other type of load, for RL load and RLE load, there is no such a condition, alpha less than 30 or alpha greater than 30. This is the common formula everywhere. For R load, if alpha less than 30, you can use this one. Alpha greater than 30, then use this one. Next, 1 second. For three-phase full wave rectifier, if alpha less than or equal to 60 degree, then this is the formula for V naught RMS. This is the most repeatedly asked question. Just to make a note, enough. Next, when we are talking about three-phase semi-converter, if alpha is less than or equal to 60, this is the V naught RMS formula. If it is greater than 60, then this is V naught RMS formula. Just have a hint. These two are very important. That's why I have covered all these things here. Next, let us talk about inductive voltage regulation. See, we are considering the effect of the source inductance. If we consider the effect of the source inductance while talking about the single phase half wave rectifier, what is the voltage regulation formula? So here I wrote the voltage regulation. We know the value of alpha and mu, overlap angle and all. So they will be giving you the value of overlap angle and alpha. Just to substitute, calculate the value of voltage regulation for single phase half wave rectifier. Here I wrote the formula for full wave rectifier also. Now, let us talk about the circuit turn-off time for all different types of circuits. First, let us take single phase half wave rectifier, and I wrote all type of load, RL, RLE load, RE load, and its corresponding circuit turn-off times here. I hope you all know alpha is the firing angle, whereas beta is the maximum conduction angle. Beyond this, circuit will not conduct. That is the maximum conduction angle of the circuit, right? For a full wave rectifier, let us continue. R load, RL load, I wrote RE load here. Wait, that another load will come. This is the corresponding circuit turn-off time. I have wrote everything here just to make a hint. Yes, fine. Next, let us talk about RLE load for a single phase full wave rectifier. It is having two connections. One is continuous connection, another one is discontinuous connection. Its corresponding formulas has been covered here. Next, when we are talking about single phase semi-converter, the most important that has been repeatedly asked in examination is RLE load. I wrote the corresponding formula pi by omega with freewheeling diode, without freewheeling diode. Both formula I have covered, circuit turn-off time with the RLE load. Next, when it comes to three-phase full wave rectifier, there also you will have to remember, if the value of alpha is less than 60, this is the circuit turn-off time. Alpha greater than 60, this is circuit turn-off time. I said I am covering only the formulas which are being asked in your examination. Next, some other things you will have to remember. When I am talking about the difference, full converter versus semi-converters. Full converters means all are thyristors. Semi-converter means it is the combination of diode plus thyristor. That is the difference. So if a circuit is having full thyristor, I am talking about full bridge rectifier, single phase full bridge rectifier. So in this full bridge rectifier, semi-converter is having two diodes, two thyristors, whereas full converter is having only four thyristors. Let us see. V naught average formula. I wrote it here, the difference. Similarly, this is fundamental source current. Its corresponding formula written here. Fundamental source current. This is just source current, not fundamental or source current, including the effect of harmonics also. Next, Let us talk about the distortion factor. So I wrote the corresponding formula here. Next, fundamental displacement factor, input power factor, total harmonic distortion. Just make a difference. Clearly note it down. Next, let us talk about the semiconductors. So in semiconductor also, as we saw, that is single phase full bridge inverter only. Sorry, full bridge rectifier only. But it is having what? Two diodes, two thyristors. You know, it is having two type of configurations, symmetrical and asymmetrical. For that, the most important question often being asked in an examination is average value of the thyristor current, RMS value of the thyristor current, average value of the diode current, RMS value of the diode current. I wrote everything here between for symmetrical and asymmetrical configuration. Just make a hint, note properly. Got it? So next, in case of three-phase full converter, the important things that you'll have to remember, apart from V0 average and V0 RMS at all, the another thing is fundamental source current formula, the output source current formula, once again the distortion factor formula, input power factor formula, then average value of the thyristor current, RMS value of the thyristor current. That's all. Now, next, let us talk about choppers. Rectifier is over. Now, let us discuss about the chopper. In case of chopper, buck converter, boost converter, buck boost converter. So only we have three types of categories. Yes, I wrote everything clearly. The relations V0 average between three people and the source average value of the source current, average value of the inductor current. Yes. Next, here I have. This is the ripple in inductor current, ripple in capacitor voltage, critical value of the inductors. For all people, I wrote separately just to make a hint properly. Right. You know the value of delta is duty cycle. All other things you know. Vs indicates supply voltage. Fine, sir. Next, let us talk about critical capacitors between all the three people: buck converter, boost converter, buck boost converter. And I have written, see, this is all over. After that, the above formula are for continuous connection. In the question, it is mentioned that if they are having discontinuous connection, then I wrote the important formula for discontinuous connection. In case of discontinuous connection, beta also will be introduced. Between alpha and beta, you will be having the connection that is discontinuous. So this is the formula for V0 average formula for buck converter. This is for boost converter. This is for buck boost converter. So I have covered all important formulas, right? So let us discuss about commutation techniques. So in commutation technique, first one is load commutation. In case of load commutation, the turn of time, circuit turn of time formula is 5 by omega t. This is called a damped natural frequency. This will be equal to omega n, that is undamped natural frequency into square root of 1 minus epsilon, that is damping ratio. I hope you all know this, right? So let us continue from this. People will be also calling it as ringing frequency. We are also calling it as ringing frequency. Sometimes in an examination they may use that word. Next, now the condition. Usually load commutation will be operated under commutation. Whereas the value of epsilon will be less than 1 and its corresponding condition. For this load commutation, the condition will be R by 2 into epsilon should be less than 1. Whereas this is the value of epsilon. That's all. Next, let us talk about current commutation and its corresponding formula. In current commutation, the peak value of the capacitor current. This is the formula. Yes. And this is the peak value of the main thyristor. We will be having two thyristors. One is auxiliary, another one is main thyristor. This is the maximum value. P indicates peak or maximum. Peak current that is flowing through the main thyristor. Peak current that is flowing through the auxiliary thyristor. Here, this is the maximum capacitor peak current. I have written the formula already. VDC, that is stands for supply voltage. Next, so this is the main thyristor turn off time, the minimum off time, circuit turn off time, and this is the maximum circuit turn off time of main thyristor turn off time, not circuit turn off time. That is the minimum off time of the main thyristor, maximum off time of the main thyristor, and then here the reverse voltage across the thyristor circuit, commutational circuit. This is the formula VDC into. They are asking the value of VR, then this is the formula. Next. So this is the circuit turn off time. So we have seen main thyristor off time, minimum time, maximum time, everything we have seen. Here I am talking about whole circuit turn off time. And the VR already formula we have calculated for VR and the capacitor current we know, just to substitute you will be getting the answer. Next here, this is the circuit turn off time of auxiliary thyristor. Here I wrote the maximum peak current. Sorry, this is completed. Next, let us discuss about voltage commutation, because the maximum peak current, main thyristor peak current I have already given for current commutation, right? So now let us discuss about voltage commutation. In case of voltage commutation, this is the main thyristor peak current. Yes, we know this is the capacitor current ICP. Same formula, ICP. Whatever the formula that I wrote here, you can take the same formula here also. Next, this is auxiliary thyristor peak current. Yes, and this is the On time, main thyristor on time formula. Yes, this is the main thyristor circuit turn off time of the main thyristor. Yes, this is the circuit turn off time of the auxiliary thyristor. Next, the most important formula is formula for minimum duty cycle. Repeatedly ask the question, and V naught average formula. These two are very important when we are talking about voltage termination. Understood? Yes, just to remember. Next, let us discuss about inverter. So in inverter, first one is single phase half bridge inverter. This is the formula for V naught RMS and generalized expression for V naught of T including harmonics, and this is the fundamental output RMS. Fundamental output RMS. There is a difference between fundamental and output. I hope you all know about it. Fine, sir. Let us discuss about single phase full bridge inverter. V naught RMS, output expression, fundamental output RMS. Next, let us talk about three phase. In three phase, we know we have 2 degree, one is 180 degree, another one is 120 degree. So for 180 degree, I wrote output line RMS voltage, the V naught, output line RMS voltage, output phase RMS voltage. This is the fundamental, that is including harmonics. This is the expression for line voltage. This is the phase voltage expression, including the effect of RMS. From that, you can express, see, this is the line voltage, including harmonic effect, we are expressing line voltage. So this is called line maximum voltage. Yes, from this you can explore. If they are asking fundamental line voltage, then replace n equal to 1 divided by root 2 and replace n equal to 1. That will give you the value of RMS value of the fundamental component line voltage. Similarly, you can repeat the same procedure. This is the maximum phase voltage, but this is nth order harmonic. For fundamental, replace n by 1. This is maximum divided by root 2 to get the phase RMS voltage. Got it? Yes. Now here 120 degree, same procedure. Output line RMS voltage. This is phase RMS voltage. This is including harmonic effect. From this is the maximum component. Replace n equal to 1 and divide the whole expression by root 2. That will be giving you the value of fundamental output line RMS voltage. Similarly for phase, you can repeat the same process. Now, let us talk about auto sequential commutation circuit. So here, commutated inverter. For this, you will have to remember only one thing, that is minimum circuit turn off time and maximum frequency. That's all. This is the sampling type formula. Very rare, just you can remember it once. Fine, sir. Now, let us have some Fourier analysis. We know our output waveform is not pure AC. It is having some harmonics effect. So when we are talking about single phase half bridge inverter, already I have given the expression for output voltage V naught of T. Now, if you divide it by impedance Z, if you divide it by impedance Z, like this, see, I have nth order impedance here and its corresponding phase angle. So, if you divide the voltage expression by impedance, it will be giving the expression for current. Similarly, for full bridge, you know the voltage expression divided by impedance and add its corresponding phase angle. That will be giving you the value of current expression for single phase full bridge inverter. Now, let us talk about the impedance. Impedance can be anything. It can be R alone, or it can be R plus j omega L, or it can be the combination of everything. So I have added everything here in general. So whatever the term that are missing in your question, suppose if they are not considering capacitor, then make this value is 0. If they are not considering inductor, then make this value is 0. So anyway, this is generalized expression for impedance. This is the corresponding impedance angle that I wrote here. Got it? Yes. 1 second. Yes. Next. Let us discuss about some other factors about inverter. First one is total harmonic distortion factor. Most important formula. We know total output RMS voltage divided by fundamental RMS voltage. Whole square minus 1 whole power 1 by 2. And voltage ripple factor. This formula you will be often using in case of chopper circuit. In chopper, you will be requested to calculate the value of voltage ripple factor. So in that case, output RMS divided by output DC voltage. Square minus 1 whole power 1 by 2. You can calculate the value of voltage ripple. Next, let us discuss about pulse width modulation technique. We know first one we are having the most important formula, single pulse width modulation. The formula is output RMS. That will be equal to supply voltage Vs into 2d by pi whole power 1 by 2. Here, this is the general expression including the effect of harmonic. Now, if the value of n equal to 1, see, this is the maximum value of the harmonic expression. If you are dividing it by root 2, that will be giving you the value of fundamental RMS, but make sure n will be replaced by 1 by calculating the fundamental harmonics. Okay. So whenever they are asking the fundamental RMS voltage for the single pulse width modulation technique, this is the maximum expression. Replace n equal to 1 divided by root 2, that will be giving you the value of RMS voltage expression. Next, the other important things, while talking about multiple pulse width modulation, remember the expression for V naught RMS, then you have to know how to calculate the number of cycles total number of cycles for each and every off cycle. Sinusoidal cycle we are considering. So for each and every off cycle, the total number of cycle will be calculated with the help of carrier frequency divided by 2 times of reference frequency. Now while talking about sinusoidal pulse width modulation, the formula will be different. So this is for multiple pulse width modulation. Specifically, if you are talking about sinusoidal pulse width modulation, this is the formula to calculate the number of cycles per off cycle of each and every cycle. Fine, sir. So here once again, carrier frequency will be given. You have to remember high frequency and low frequency signals. While talking about sinusoidal pulse width, high frequency will be triangular, low frequency will be your sinusoidal signal. The most important term will be modulation index, and here I have given that is reference voltage divided by carrier voltage. The ratio will be giving you the value of modulation index formula. I hope I have covered everything about power electronics. So with the help of these all formulas, if you remember all these formulas in your mind, I am giving 100% assurity. Mostly I can give at least 8 marks you can easily gain out of 10 marks. Maybe some of 1 or 2 questions you may miss, but all other formulas I have covered. Just to go through it again and again multiple times and learn how to apply these formulas into problematic into problems. Practice as many questions as possible. Definitely it will be helping you to crack all upcoming exams. So further, if you have any doubts in this, if you are finding something, if you want, you can drop always in the comment section. Your queries or doubts will be replied shortly.